Hi, in this lecture series we are going to discuss about heat transfer. As you can see, heat transfer is made of two words, heat and transfer. So question arises, what is heat? Heat is defined as an energy in transition which flows from one region to other region solely due to temperature difference. What do we mean if we have two bodies? Let us say A and B, and we assume that these two are in contact. Then there will be a heat transfer either this way or this way depending upon the temperature difference. If TA is greater than TB, heat will flow from A to B. If TB is less than TA, then heat will flow from B to A. This is known as second law of thermodynamics. That is, heat transfer occurs as per second law of thermodynamics. This is important. Heat transfer we can define it as a branch of science which deals with the determination of rate of heat transfer. Heat transfer rate, if this is a body, let us say body A in which heat is flowing, and we says that 10 watt heat is flowing in this body. So the question arises, in which direction the heat will flow? Heat can flow either in this direction or in this direction depending upon the temperature difference or temperature profile within the body. Hence, heat transfer rate is a vector quantity, that is, it has magnitude as well as the direction. So, heat transfer rate is a vector quantity. The rate of heat transfer per unit area is called heat flux. That is, Q dot is Q dot upon K. It has a unit watt per meter square, In this relationship, this is the heat flux, this is the rate of heat transfer, in watt, and this is the surface area through which heat transfer takes place. The rate of heat transfer, the rate of heat transfer is strongly dependent upon modes, or we also say it as mechanism of heat transfer. There are three modes of heat transfer. Three modes of heat transfer, namely conduction, second one is the convection, and the radiation. Now we will discuss conduction in brief. So conduction is defined as that mode of heat transfer in which heat energy is transferred from one energetic particle to adjacent less energetic particle. What do I mean is, so conduction is mode of heat transfer in which heat energy is transferred from one energetic particle to adjacent less energetic particle. Let us consider a solid lattice. And this cross section is the molecular position. As we know, in solids these molecules keep vibrating along its mean position. So this one can vibrate, this molecule can also vibrate, similarly this one and this one. During vibrations, this molecule will transfer some amount of energy to this molecule. Similarly, this molecule may transfer some amount of energy to this molecule. So this mode of heat transfer is known as conduction. And one other thing is, in a solid lattice, there can be some amount of free electrons. When these electrons moves, this can also transfer or carry some amount of energy from one region to another region. This is also a source of conduction. Okay. So conduction can take place in solid as well as in liquids. In solids, conduction takes place due to molecular vibration and flow of free electrons. Whereas in liquids, conduction is due to molecular vibration, molecular diffusion and molecular collision. Conduction is a microscopic phenomenon. Why we are saying it is a microscopic phenomenon? Because it depends upon the motion or kind of motion of molecules. Let us assume we have a body or medium, and we are assuming that this is a body, okay, and we are assuming that assumption first one, only 1D heat transfer. Second one is heat transfer in this body is taking place only in one direction, let us say x direction. This is 1D heat transfer. Okay. Second one, we are saying that it is a steady state. What do we mean by steady state is there is no temperature variation with respect to temperature is not a function of time. Okay. Temperature of the body is not a function of time. This is the steady state. Third one, boundary of this body is at uniform temperature. Third one, we are assuming that what do we mean by uniform temperature is at this boundary, let us say at any time this temperature is T1. That means at all the points along this boundary, here, temperature is T1. Similarly, let us say at this boundary, temperature is T2. So at all the location along this boundary, temperature is T2. And let us say this surface area is A. Then the rate of heat transfer due to conduction without any internal heat generation is given by Fourier's equation, which is Q dot conduction is minus Ka dt upon dx, where A is the surface area perpendicular to the direction of heat flow. Dt upon dx is the temperature gradient in the direction of heat flow. The negative sign indicates that heat transfer is positive in the direction of heat flow. K is the thermal conductivity of material. Its unit is watt per meter Kelvin. This thermal conductivity is strongly dependent upon temperature. And in this equation, let us say equation A, in equation A, K is assumed to be constant. Okay. K, that means thermal conductivity is a material property it is also a transport property. The value of K indicates the amount of heat transfer rate within a medium. Value of thermal conductivity varies with material as well as the temperature. So there are some facts regarding thermal conductivity. The first point is thermal conductivity of metal or pure metal is always greater than the thermal conductivity of alloying metal. Second point is the mechanical forming decreases the thermal conductivity of the material. That means thermal conductivity of a hardened steel is less than thermal conductivity of the annealed steel. Metals conductivity K decreases with increase in temperature except aluminium and uranium. Fluids conductivity K decreases with increasing temperature, except water. So the thermal conductivity of any material is written as K is equal to K naught 1 plus alpha T, where alpha is known as coefficient of thermal conductivity. For metals, alpha is negative. For liquids, alpha is negative, except aluminium and uranium. For aluminium and uranium, alpha is positive. For water, alpha is positive. The highest thermal conductivity is of diamond. Diamond has highest thermal conductivity, which is equal to 1300 watt per meter Kelvin. The lowest thermal conductivity is of freon. Freon is a refrigerant. Okay. Freon has the lowest thermal conductivity and its value is equal to 0.083 watt per meter Kelvin. Now we will briefly discuss about convection. It is a mode of heat transfer between solid surface and liquid. We can say it is a fluid if it is in bulk motion. What do I mean is, let us say a surface having temperature Ts and some fluid is flowing over this surface. And this fluid initially has a temperature of T infinity. When it comes into the contact of solid surface, it tries to take some heat from solid surface or tries to give some amount of energy to the plate depending upon the temperature T infinity of Ts. Let us say Ts is greater than T infinity. Then the heat flow will be from surface to liquid Q dot. So, if this liquid has some amount of bulk motion, then the heat transfer from the surface to liquid is known as convection heat transfer. So, convection is divided into two parts. First one is the forced convection and second one is the free convection or natural convection. The forced convection this is defined as when the fluid is forced to flow by external means, then it is known as the forced convection. As in this case, let us say this is a hot surface which has temperature Ts and surrounding air is forced to flow via a fan. This fan is rotating. This fan will force this air to flow in this direction. So this is an example of forced convection. Whereas the free convection, fluid motion is due to density difference between the two layers. Let us say this is a surface having temperature Ts, its surface area is As, and some fluid is flowing over the surface whose free stream temperature is T infinity, fluid temperature. Then the rate of heat transfer is given by Newton's law of cooling, which is Q dot convection is HA Ts minus T infinity, and it has the unit watt, where H is the convective heat transfer coefficient, and it depends upon many variables like geometry of the surface, fluid properties, Newton's law of cooling is Q dot convection is equal to H Ts minus T infinity, where H is convective heat transfer coefficient and its unit is watt per meter square Kelvin. A is surface area perpendicular to the direction of heat flow. Ts is the surface temperature of solid, and T infinity is the temperature of fluid very far from the free surface. We refer from the surface that is solid surface. Okay. The convective heat transfer H depends upon fluid properties like viscosity, specific heat constant Cp, thermal conductivity K, density, etc. Flow properties like velocity of the fluid, geometry of the surface, the heat transfer taking place from a horizontal surface will be different from the heat transfer taken from a vertical surface. Vertical surface. This is the horizontal surface. Q dot convection, horizontal, Q dot convection, vertical. When we compare these two for the same fluid and flow properties, this Q dot convection will not be equal to vertical. And so at the end, we can say that convection is a macroscopic heat transfer. Now we will discuss about third kind of heat transfer, that is radiation. It is the energy emitted by any matter in the form of electromagnetic waves. Radiation heat transfer. The radiation heat transfer can take place in vacuum also. What I mean, if let us say this is a room, a body is hanged from the ceiling, which has temperature Ts, and this room wall has a temperature of T infinity, and the room is evacuated completely. That is, there is a vacuum inside the room. After some time, when we measure the temperature of the wall of room, what we see, the temperature T infinity will increase. That means some amount of heat transfer is being taken place between the surface and the wall. This is nothing but the radiation heat transfer. Radiation heat transfer. By this example, we can say that radiation does require any medium. Heat transfer by radiation, heat transfer by radiation takes place at the speed of light. Let us consider a body A whose surface area is S and its emissivity is epsilon. Emissivity is a surface property which we will discuss in detail in further chapter. Emissivity. S is the surface area. It has unit m square, meter square. Emissivity, this is a non-dimensional number. Non-dimensional. And let's say its surface temperature is Ts. Then the radiation emitted by any surface here is surface A is given by Stephen Boltzmann law, which is Q dot radiation is equal to epsilon times AS sigma B to the power 4, where sigma B is a Stephen Boltzmann constant. This is equal to 5.67 into 10 to the power minus 8 watt per meter square Kelvin or 4. That means this surface will emit energy in all these directions. This is in the radiation. And the last thing about radiation is it is a surface phenomenon.